Like I said, when we're dealing with logarithms, you can technically make any value the base, which means you have tons and tons and tons of different logarithmic functions. But to make our lives easier, there are really only two bases that are particularly relevant: log base 10 and log base e. Where log base e is a thing called the natural exponential that we're going to finish the section with, and log base 10 is what's called the common logarithm, where this idea came about from collaborations between Napier, who we mentioned earlier, and Henry Briggs, where we have the notation for log base 10, because it's a special value, as just log of x, where in some contexts you might see this notation also used for the natural logarithm and some other variations upon it, but in our notation we take this common version there because that's the way that engineers generally referred to it, so that's how it ended up on calculators, and that's how it's generally written. But for reasons we'll see later, really this one's not too important anymore, with a thing called the change of base formula that we will be seeing in the next couple of sections. And the natural logarithm, we don't actually have to talk about anything except for the natural logarithm, but this one is kind of a natural one, its own right, to talk about for the fact that it is base 10, which means it works in the same types of things that our numeral system works in. That is, powers of 10 that we write in terms of our digits. This also thinks in terms of digits, but it's a little bit of an antique. Anyway, we'll see one way that this is used still in a modern context. So the magnitude R on the Richter scale of an earthquake with intensity I is given by R equals the common logarithm of I over I naught, where I naught is the minimum intensity of an earthquake. The largest earthquake in Florida's history was 10 to the 5.9 times as intense as the minimum at its epicenter in the Gulf of Mexico. What was the magnitude of this earthquake on the Richter scale? So working with the Richter scale is kind of a traditional example that uses the common logarithm, and it's what we're going to see here. For this, we have that the value on the Richter scale, R, is equal to the common logarithm, as we said, of I over that I0 or I naught value, where in this case we are told that we have I is 10 to the 5.9 times I naught, that it is 10 to the 5.9 times stronger than the base of that I naught value. The I naughts cancel, and we are left with log of 10 to the 5.9, the common logarithm of 10 to the 5.9, where remember, the common logarithm is log base 10. We have log base 10 of 10 raised to a power. Logarithms are all about identifying exponents, so this would just be a, up to my marker working, 5.9 on the Richter scale. That's how we would identify that power there, where it's a decently large earthquake, not the biggest ever, and certainly be pretty unusual if something like that happened again in Florida, because we're not used to those. But that's what we would have here, using the common logarithm as our representation. And the very last thing we get for this section is a look at the most important logarithm, at least the most important one for modern math, the natural logarithm, log base